Hi everybody, welcome to another video in Statistics, Chapter 4. In this chapter, we'll describe the relation between two variables, and the variables are the response variable and explanatory or predictor variable. So one of them is the x, the other one is y, and we plot on the xy coordinate and to see the relation between the two variables. So that's what we call the scatter diagram. It's a graph that shows the relationship between two quantitative variables measured on the same individuals. Right. So once again, two variables, one of them is response variable and the other one explanatory or predictor variable. And both of those variables come from the same individual. Each individual or a data point is a set represented by a point in the scatter diagram. So pretty much plot that in the xy coordinate. So let's look at the first example. The data shown to the right here are based on the study of drilling rock. To drive real distance of 5 feet in rock increase with the depth at which the drilling begins. So that could be two variables. One of them is the depth and the other one is the time to drill 5 feet in 1 minute. And so it depends on where we start at the depth x, the time to drill the next 5 feet will depend on that. Of course, when it getting deeper and deeper, the time will be more and more. It will be more difficult to drill. Right. And with that, we have this table. And if we plot that on the scatter plot, one is the depth. So this on the x coordinate. And the y coordinate is the time to drill 5 feet. Y. So the time and then the depth. And we plot those points, and that's what we have. So based on this, of course, we can see that the time to drill the next 5 feet will be more difficult as the depth increase. But not really well related, kind of all over the place, as we compare the relation between the points, between the variables. If it's like this, then it is strongly related between the explanatory and the response variable. And that is called the linear relation, because that's more like a line. Next we have the nonlinear, kind of a curve or a curve. And when there's no relation, when they just scatter all over the place. So when there's no relation between the variables. So we say two variables are linearly related, are positively associated when above average values of one variable are associated to the above average values of the others. So this is called the positive related or positively associated, because like the line going up, and this is negative related when the line goes down. So positive going up, negative going down. Right. So this is just the way to describe this situation, but of course when we graph it and we see so this looks like that's positively related, but not very good related. As supposed to this will be a lot more closely related or closely positively associated, and this is negatively associated. Right. So of course when we say properly positively associated, we mean if one increase, the other one also increase. So one variable increases, the other variable also increases. Now negatively associated, if one increase, the other one decrease. One variable increases, the values of the other one decrease. So positive, negative. Right. Now let's look at this example. The phone data are the final exam score of 10 randomly selected history students and the number of hours they study for the exam. So let the hours of study be x. So this x. So we say hours of time study or hours of study. And the other one will be the score. Right. For the time for x hour, we will go from 0 to 8, the maximum. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Oh, can make that double. Okay, just choose 2, 4, 6, 8, and 10. Right. On the score, if we want to go from 0 and the maximum grade look like 90, so 10, 20, 30, 40, 50, 60, 70, 80, 90. Yeah, that's perfect. 100 is here. And 20, 40, 60, 2, 4, 6, 80, sorry, 100 could be here. Right, so we plot 3 be 65, 5, 80, 2, 60, 8, 88, 2, 66, 4, 78, 4, 85, 5, 90, 6, 90, and 3, 71. So as we see the point here, it looks like it is positively associated as more hours study have the better score. Now, because that's what we do by hand, that would be easy. How do we do that on the calculator? So on calculator, we're going to turn on the scatter plot, hit second, y equal 2, and the plot, turn it on. It's very important that when we're done this, we have to go back and turn it off. So the plot, the first one is the scatter plot. We're going to keep that. Right, that quick. Hit start, and then enter the list. So 3, 5, 2, 8, 2, 4, 4, 5, 6, 3. Right. Now we go to L2 and we enter this for Y. 65, 80, 60, 88, 66, 78, 85, 90, 90, and 71. Right, so enter the axis onto L1, list 1, and Y into list 2. Right, second mode, back to home screen. Again, to turn it on, second stat, the first one, just hit enter and choose on. The scatter plot is this one, and then just use that pattern. So it's good. Second quick. Of course, when you hit graph, won't be able to see anything because we have to adjust the window. To adjust the window, hit Windows. On the x-axis, we go from 0 to 10. I would say it's better to choose a little bit on the left a bit. So don't choose 0. I choose -1 instead. So we have something kind of like this at the corner. Point. It look better. So -1 to 1 on the x. The increment is 1. That's good. On the y, I can go from -10 to 100. And the increment will be 10 for each ticks. Each tick will be 10. Right? Hit graph. Now you see the scatter plot will be like this. Right? Okay, let's see how do we do that on the StatCrunch website. We switch and we go to StatCrunch calculator. Right, so I will enter 3, 5, in column 3, 5, 2, 8, 2, 4, 4, 5, 6, 3. And then second one, 65, 80, 80, 60, 88, 66, 78, 85, 90, 90, and 71. Right, and then we'll go to graph. And we see the scatter plot here. Scatter plot. X variable, we choose variable 1 for X and variable 2 for Y, and then just compute. We should see the plot. For the scale a little bit off. So let's do that again. Graph, scatter plot. First, second. Alright, is there an option to choose the scale? No. Let's go back on option. Can we edit? Nope. Yeah. See x-axis. Yes. We can choose. Click on the bottom here. We can change. Say from -1. The maximum 10. Okay, and now click on that again, go to y-axis and then go minimum of -10, go to 100 and okay. Yeah, that's better. So that's exactly what we have. Again, we enter the data here and then hit graph and choose scatter, and then we plot it. So whether we use the calculator or the StatCrunch calculator will be the same thing. Right, now we go back to the section. Like I said, when we're done with this, hit second stat plot and turn it off. Otherwise, it will do some strange behavior. Right, and then mode. When we hit y equal, this should not be highlighted. When it turn on, it will be highlighted. So the default should be like this. When on the stat plot, turn off. Right, so we plot the points. What else can we tell from it? Of course, we can tell that it is positively associated, but is there a number to put in it to tell how they related? And course, the answer is yes. So what we define is called the linear correlation coefficient, or the Pearson product moment correlation coefficient. I'll just stick with the first one. So now this R represent the linear correlation coefficient, and the formula is that the S is standard deviation, the X bar of course is the mean. Yeah, so that is the formula. Kind of complicated if we have to calculate every single one by hand. Alright, so and we have some properties here. So we calculate that R, and if that R, the values will have to be between -1 and 1. If it is equal to 1, it is perfectly positively linear relation, or the positively correlated. If it's equal to 1, if it's equal to -1, it is perfectly negatively correlated. And then if closer to 1, it is the strong evidence that they are positively associated. And if it's close to -1, it is close to negatively associated, right? So this is exactly 1, this is exactly -1, this is close to 1, and this is close to -1. And when there is no relation, that could, the R will close to 0. Right. So once again, just go back review what we have in this section. So this section, what we have is just we have the pair, the set for each data point that with two things related for each individual. So from certain values of x, a point it will be an x and y. Just like this, there's certain student for particular some time spent on study and the score. So this will be come from one student, this will come from another student. Right, and then we can calculate that to get the linear correlation coefficient. Alright, now determine the linear correlation coefficient of the real data. Let's not do that. Let's use let's use this data instead, because we already entered that in the calculator. So coefficient of the data in example 2. Right. So this is data in example 2. So on the calculator we still have that, is that, edit. So these are the data. Right, now we find the linear correlation coefficient. Alright, how do we do that? So is that calculate linear regression, and list 1, list 2, and calculate. Did not give you anything, don't worry about that. What we need to do is we need to turn the diagnostic on. We only need this to do one time on your calculator. Second, catalog. I don't know where it is, so I have to look it. Go to diagnostic. Diagnostic on. Hit enter one more time. That's it. So once again we have the two lists. List 1 we store the x values, list 2 we store the y values. Now we start calculate linear regression, choose this one and then calculate. So the x is L1, y is L2, calculate. And now the R is 0.8465. So we use linear regression that we study in the next section, by the way. We have R equal to 0.8465. So this number is close to 1, so they close to positively associated. Right, so where is that? In the StatGrunch, right? So remember, we still have the data from in the StatGrant. So we go to stat, and then compute. Just go to regression and simple linear, and then we choose x will be the first variable, y to be the second variable, and we'll just skip everything. Don't worry about that, just skip that, and then compute. And I'm not sure if you can see this. Look. Yeah, much better now. So when we do that, we can see it said R correlation coefficient 0.8465. Yeah, so that's what we have. Once again, is it under stat, regression, and then choose simple linear, and then first variable for x, second variable for y. Right, so and we'll get that number. Right, here's a few notes about that number. Right, critical values for correlation. So we say that depends on the number of points. If it is high enough, then there will be some relation. So we have a previous example, like this example, we have 10. I'm sorry, I'm looking at the note. Right, now critical values for correlation coefficient. So if we have 10, like last example, we have 10 students, it have to be more than this number to show that they are related, and so it show that they are related. Right, now here is an example. According to the data obtained from the Statistical Abstract of United States, the correlation between the percent of female population with a bachelor degree and the percentage of birth of unmarried mothers since 1990 is, so the number is very high. So does that mean that the percent of female, does that mean that these two quantity related? And the answer is not. It's very important to know that even though the number are strongly related, but they actually may not causing the others. The number are related, yes, but doesn't mean that one causing the other to happen. That's very important. So we say that the correlation exists only because both percentage have been increased in 1990. So it is this relation that caused the high correlation. In general, a time series have high correlation. So, like I said, just because the number relate, they show that strongly associated, positively or negatively, doesn't mean that one causing the other to happen. So correlation does not imply causation. That's the way they usually say it. So when there are observational, we cannot claim the causation relation between two variables. We can claim that the data are related, but just the data, but not actually related. All right. Another way to look at this is through the lurking variable. We define that in the first chapter. Right, here is another example. Ice cream sales and crime rates are very high correlation. Does that mean the local government should shut down all the ice cream shops? Of course, that's not, because usually the ice cream sales and the crime rates are high during the summer, or the temperature rises. Both of them will increase, so they have nothing related to each other, but just happen to increase at the same time over time. Right. Now here we have another example. Yeah. So because of colas tend to replace the healthier beverage, and colas contain caffeine and phosphoric acid, which is not good for the health. So this table lists the type of number of cans of soda consumed in a week, and the femoral neck bone mineral density of for example 15 women, the data collected show like this. So the correlation between the number of collars per week and the bone mineral density is negative 0.806. That means the more collars consuming, the density will decrease. And furthermore, the data are collected group of study we surveyed with including those lurking variable as well. So I said this may or may not happen, but those variable might affect the actual density of the bone as well. So bottom line, what we learned in this section is that for the type of data when we have one individual with two variables, and we're trying to see if those two variables are related, even though if they are related doesn't mean one variable causing the other to happen. And we use the linear correlation coefficient to determine how well they are related, and that number is between -1 and 1. If it is 1, it is perfectly positively related. If it is -1, it is negatively related. Right, now, so that section will tell us if the data, if the two variables are related. Now, this section will tell us how well they are related and can we make a prediction if they are related. Alright, so let's look at this example. For the phone data, we just have x and y, we have this coordinate. So let's plot the points and see if they are related. So 0 and 5.8, x equal to 0, 5.8. X equal to 2, 5.7. Three, 5.2. And 5, 2.8. 5, 2.8. 6, 1.9. And 6 again, 2.2. Right, so that look like they are negatively associated. Now, and then next is the question is, can we draw a line that closest to all the point? Let's just loosely say that it's closer to every point, or the proper name is the best fit line. So the way we do that is just draw a line, of course, close to the point, and the rule of thumb is we choose the same number. Let's say if we draw a line and there are 6 points, make sure that we have 3 points above it and 3 points below it. Okay, so it's about here, for example. You have 3 points above, 3 points below, and even though it's the line further from this point, but it's actually closer to that point, so it might be more like this. Okay, like that. It will be very difficult to get exact answer to do this by hand, but this is the best fit line we have. Now, how do we set the equation if we can come up with this equation with the line? So now, to find the equation with the line, first we have to find the y-intercept, where to intercept the y-axis. So it look like here, I would say if that's 6, the 7 about here, so about I should not use the same color. This is this point. It look like on the y-axis it is about 6.75, right? And then how do we determine the steepness of the line, or what we call the slope? So in algebra, we define the slope is the change in y over the change in x. So let's say I pick when x equal to 2, I pick this point, y is equal to 5.25. Like I said, we won't be able to do this by hand. The calculator can do that, but if we do it by hand, this is how it goes. So we choose some values for x and for y from that best fit line here. If we choose x to be 2, look like it's 5.3. If we choose 4, it's about 3.6. Remember, we just only estimate here. Right, and we use this formula. So the slope will be equal to the y values minus the y values, 3.6 minus 5.3, and then 4 minus 2. Right, the same y minus the y, the x minus the x. Don't switch the data. So both of these come from a point. Both of these come from a point. Right, 3.6 minus 5.3. I'll just put the whole thing in the calculator. 3.6 minus 5.3. Close, and then divide by 2. 4 minus 2. So I have negative 0.85. So we find the slope, and then this is called the intercept or y-intercept. It intercepts the y-axis. So the equation will be y estimate equal to the y-intercept, or we say the slope, times x plus the y-intercept. Right, so that, again, the slope is this, and the equation of the best fit line is in that form. So in this particular, we have y equal to the slope is negative 0.85 times x plus the y-intercept of 6.75. So the significance of this is, let's say in this data we are not given when x equal to 4. When x equal to 4, if we put 4 in here, we have the values like negative 0.85 times 4 plus 6.75. Yeah, I have 3.35. So based on this equation, we can make the prediction of some value for x. Alright, now let's see if we can do this on the calculator. So we start, and I will clear this data, clear the list, highlight the list, hit clear, and then enter. Highlight the list, hit clear, and then enter. Now enter the new number 0, 2, 3, 5, 6, and 6. 5.8, 5.7, 5.2, 2.8, 1.9, and 2.2. Right, and then second, not quick, then go to statistic, the start button, calculate linear regression, option number 4. X variable list 1, y variable list 2, and we calculate. Yeah, so we have the correlation coefficient, so that's very highly related, and then we have the equation. So according to this, the calculator, the actual what we have from the calculator is y equal to negative 0.71 x plus 6.55. So the calculator will have this answer, and we estimate by hand, we have that answer. Of course, the calculator is the exact answer, and we just based on the graph, it's just approximation. Right. Right. So, of course, all the details here is, so what we actually do is, what we try to is we find the line, and then we find the distance between the line and the point, and we try to minimize the sum of all that distance. And when we do that, we have the equation, and the equation of this square regression line is given by that. Of course, we covered earlier when we do it by hand, but if we want to do that exactly, we use this. Again, the S is the standard deviation, and then the equation will be given in that form, right? So to come up with the equation, that's what we do. Right. A few things I need to cover that to make sure that if you're not using this calculator and it look a little bit different, let's say when you hit stat and this is what you see, we can store the equation too. Let's say we store the equation into y1, hit variable, y variable, function y1, and we store the answer y1, and when we calculate, when you hit y equal to, we have the equation that times x. Right. Actually, it doesn't matter what mode your calculator is on. Should be fine. Just linear regression. Right. Now go back to the start current calculator. See how we do it. Right. Let me clear this data, and I enter the exact data we have on this example. Right. 0, 2, 3, 5, 6, and 6. Second variable 5.8, 5.7, 5.2, 2.8, 1.9, and 2.2. Right, and then we'll go to stat and regression, simple linear. So that's exactly like what we did earlier. Choose variable 1 for x, variable 2 for y, and just roll down, and we don't need to make any adjustment, just let's compute. Right, so what we have is, of course, we have the R correlation coefficient is that, and we have the equation, which is exactly the equation that we have if we're using the TI calculator. Right, now go back to the notes. Now, next, so the question is, why do we need to find the equation of this line? Well, when we find the equation of a line, we can make prediction. For example, here we have the data from 0 to 6. We don't know what is equal to 4. So when we have 4, we can estimate what will be the y values corresponding when x equal to 4. Right, now, this note here says that if the least square regression line is used to make prediction, that's usually the case. And if the variable are much larger or much smaller than the observed values, then we say that outside the scope of the model. And we never use a least square regression line to make prediction outside the scope of the model. For example, if it is like this, and you say what happened, what y equal to when x equal to 10. Remember, we only have data from 0 to 6. Outside of that, the data, the prediction will not be good. If it is close, one thing we say 7 or something is close enough. But if x is way outside, this prediction will not be good. So only make prediction when it is within the scope of the model. Right. So remember, we have the data for this on the previous section, where I have the time study and the score. That, let's find the least square regression line for that. So again, stat and edit. Now I need to enter those data again, or just sort of kept it. Anyway, 3, 5, 2, 8, 2, 4, 4, 5, 6, 3. Faster to type with the keyboard than use the mouse. 65, 80, 60, 88, 66, 78, 85, 90, 90, 90, 90, and 71. Right, and when we're done, hit second mode, and then go to stat, calculate linear regression. Remember, on the previous section, we already turned the diagnostic on, and we only need to leave that on. We don't, unless we turn it off, it will be off. Otherwise, it will stay with the calculator. Right, so L1, L2, I will actually store this into store equation into y1 alpha trace y1 and calculate. All right. So we have, remember, we have the correlation coefficient, and now the equation is y equal to a times x. So this is a, I'm just going to say 5.044 x plus b is 56.11. Right. Now I remember what I need to show is to do this with a different calculator. Right. I'll switch the calculator here. So stat, same thing. Edit. 3, 5, 2, 8, 2, 4, 4, 5, 6, 6, and 3. Next, 65, 80, 60, 88. Okay. 60, 88, 66, 78, 85, 90, 90, and 71. I shall enter those data in once again, second mode. If you're using this calculator, it might look a little bit different. Statistic, calculate, number 4. Right, I guess it's fine. But again, I forgot to turn the diagnostic on for this calculator. Right, once again, second stat, sorry, just stat, and calculate linear regression. If you want to specify different values, you can say second 1 for L1 and second 2 for L2. You only need to do this for this this calculator, right? Yeah, and calculate the same thing. This time we have the R as well. And we said why this calculator and also the calculator the stat range also give us the R square values. And here we have the R square values. Well, that's what we look in the next part of the section. It says that the coefficient of determination R square measure the proportion of the total variation in the response variable that is explained by the least square regression line. So if we have that R and we square it, that number will be between 0 and 1. And any square cannot be negative. So that's why it have to be between 0 and 1. If it is equal to 0, they have no explanatory values. If R square equal to 1, that explains very well. So just like what we have, the R, if close to 1, is very well correlated. If it's close to 1 or negative 1, they're well correlated. Close to 0, they're no related at all. Right. And determine R square. This only works for if it is for the linear regression model. Right. The R square here is exactly equal to the R, the coefficient correlation square. So that R square is equal to this R square. Of course, when we look at this, when we hit the stat, calculate, there are a lot of other regression, linear regression, quadratic. So bottom line is we sometimes we do not want to fit the straight line. We might fit a curve, a different type of curve into it. But in this linear regression, whenever we have the r and the r square will be one is the square of the other. If it is different relation, we won't be able to have it. By the way, just want to show you how that actually works. Remember, we store the equation. We did not. Right. The equation is 5.044x plus 56.11, right? So that equation. Right. Now how do we see the best fit line with the stat plot? Remember, what we still have is the x and the y data here. So what I'm do is I'm hit the Windows one again. I will change from -1 to 10 for x and -10 to 100 on y, and we see that is the line. Now to turn on the stat plot, second stat plot, turn it on, and then graph. You see those are the points, and this is the best fit line, the line that is closer to all the points. Right, now if we hit y equal to, you see the stat plot is on. When we're done, make sure that is off. Again, second stat plot, turn it on, and we choose the first one is the scatter plot, turn it on. X is L1, Y is L2, so that's very just on. And then when we hit graph, we see it. When we're done, second stat plot, highlight off, and then you see it will not graph the point anymore, and when you hit y equal to, it does not highlight any of the plots. That's what we need. Right, so bottom line is we have the x and the y, and we find the equation of the best fit line, and we calculate r to see how well they are related. Right, here is another example. In an area of the Great Plains, the record for rainfall in inches and the yield of wheat in bushel per acre was like this. Now compute the sum of the square residuals of the least square line of the given data. Right? Okay, actually we're not doing that. What we're doing here is I'll find the equation of the least square regression line, right? And after that we find the linear correlation coefficient and the coefficient of determination, which is the square of the correlation coefficient, and then we estimate the yield if the 9 inches of rainfall. Right, so for this I will switch to the auto calculator. Right, so we have the rainfall is x, the other one is y. So stat, edit, now we enter the data. Okay, 10.5, 8.8, 13.4, 12.5, 18.8, 10.3, 7, 15.6, 15.6, and 16. Right. Check. 10.5, 8.8, 13.4, 12.5, 18.8, 10.3, 7, 15.6, and 16. Right. Next, we enter the second row for y values for list 2, 50.5, 46.2, 58.8, 59, 82.4, 49.2, the screen look different, but that might be I actually hit something. 76, 78.8. Right. Right, and second stat. Sorry, quick first, second mode to quick, and then stat, calculate one variable, number 4, and let's store the equation. If you have that option, always do that, so it's easy to work with. Variable, y variable, function, y1, right, calculate. Oh, right. So I reset the calculator, so I have to turn the diagnostic on one more time. I don't know why they left that option. The default should be on. Alright. Now stat, calculate linear regression, and store the equation. And calculate. Right, so we have everything. So we can say the equation y hat, because that's just an estimate. A will be 4.379 times x, and B plus 4.267. Right, based on that answer. Right, the linear correlation coefficient, that R is 0.98, so that's very well related. And the coefficient of determination, that R square, big scale will be just the square of the order, 0.962. Right, so that's very well related. And the next question is, estimate the yield of width for 9 inches of rainfall. Right, so the data here we only have between 7 and 16, which is good. Between 7 and 18.8, the 9 is within that range, within the lowest and highest value, so this is very good. So we can make prediction based on that. If we want to predict for like 25 for x, it's not in the scope of this data. Right, so the width, the yield width in 9 inches of rainfall. So what we do is we use this equation, so we can say 4.379 times 9 plus 4.267. So we just put 9 in for x, pretty much. 4.379 times 9 plus 4.267. 43.678. So it look reasonable. Yeah, if we have something outside of this range, then that might be a problem. Right, one more thing though. We only store the equation into variable, right? y1 already have that. So if we store the equation into y1, all we need to do is recall the y1. So variable function, variable y variable function y1. Yeah, let's do that again. And all we need to say is open parentheses and 9. So that means when x equal to 9, evaluate the function, and that gives us that value. Right, so the calculator answer, this answer is a lot more accurate than the one we have here, because we round up 3 decimal places. Right, so this chapter we learned about the relation between two variables, and even though they are related, they might not be the cause of one might not cause the other to happen. And second, we can find how well they are related based on this coefficient. And after that, we can calculate the linear regression, so we can make prediction. And that's all I want to cover in this chapter. Thank you for watching and see you in another video in statistics.